Afternoon. It is a pleasure for me to introduce Tomáš Bodnár from the Czech Technical University. Tomáš is a well-known expert in numerical mathematics, in particular in simulations of fluid flows of various kinds. And today he will speak on the strain-based hemolysis models in the context of viscoelastic fluid flows. So please take
Okay. Thank you very much, Peter, for the kind introduction and for the invitation to come here. So this presentation is kind of a combination of some old work and some new ideas, but I apologize, you will not see many results. It's mainly about the models and partially about some numerical algorithms, how to get the results that will be presented later on somewhere else. So I will start, we will speak about blood. Blood is a quite complicated fluid, and what will be very important for us today is partly the viscoelastic behavior, the shear thinning behavior, and the behavior of and properties of red blood cells. So this is kind of a standard picture that you can find in many books that explains how the blood behaves under in the shear flow. So you can see that there exists a significant drop in the viscosity, increasing shear rate for the blood. And they were trying to, let's say, figure out what is the reason behind it. So this phenomena, which is called shear thinning, so it's really thinning with increasing shear, can be partially attributed to aggregation of red blood cells. So if you prevent the red blood cells from aggregation, so we'll get the lower curve, which is much more flat. And partially, the shear thinning can be attributed to deformation of red blood cells. And again, if you add some hardening agent, that will make the membrane of these cells less elastic, so you will get almost flat curve. So it's really kind of explains how this property of blood, this shear thinning, can be attributed to the combination of aggregation and deformation of red blood cells. In fact, it's a little bit more complicated if you see here these micro pictures. So this is under 0 or very low shear rate. The red blood cells form this columnar structure, which then increases the apparent viscosity. If you increase the shear rate, you will separate the red blood cells into individual cells. So it's just a suspension of red blood cells. And then if you keep increasing the shear rate, you can observe the elongation or let's say elastic deformation of the red blood cells. That's not enough for blood, so it will be still too simple because the same behavior like here for viscosity, so it's changing behavior with the shear rate. We can observe the same kind of variable elastic behavior in blood. So blood is in fact not just viscous fluid, but viscoelastic fluid. It's a matter of question whether we should or should not consider in practical applications the viscoelasticity or the elasticity itself, but for the purpose of this presentation, it's important. So this is how the blood behaves. If you try to convert it into equations, so this is really too elementary probably. So you can play with the shear stress versus shear rate for the Newtonian or generalized Newtonian fluids, where the slope of this curve is the viscosity. In case it is constant, we speak about the Newtonian fluids, but for the blood, as mentioned previously, the behavior is more complicated. So the stress versus shear rate curve is possibly one of these curves, where for the Newtonian you have the constant slope, which corresponds to constant viscosity, independent of the shear rate, but for the shear thinning fluids, the stress versus shear rate curve looks much more like this. So if you translate it into slopes, you will get something that you can see here. So you start with the higher slopes or higher viscosity that will then decrease. Of course, for blood, it's difficult to prescribe some function for the viscosity of this kind. So you start from the viscosity mu0, which is, let's say, 0 shear rate limit. Then there is some fast change into some asymptotic value, which is considered to be mu infinity as the viscosity for the close to infinite shear rate. So for the shear thinning fluid like blood, you will get this kind of a curve with variable viscosity. But still, we consider that the stress tensor is directly proportional to rate of deformation tensor. So if you take a look here, so these are just different formulas for the viscosity. This is not the key point for this presentation today. So it just shows that there is plenty of these formulas. But if you use the same values of mu0 and mu infinity, then all these functions will provide very similar results that you cannot distinguish one from another. The major problem is to measure the viscosities, not to fit the curve. We will be much more interested in more complicated fluids. So the Newtonian fluid corresponds to this kind of behavior that is characterized mechanically by a single dashpot with only viscous relation between the stress and shear rate. Here, for the first viscoelastic fluid is a combination of the viscous response and the elastic response. For blood and other kind of polymeric fluids, it's difficult to use the Oldroyd type fluids, which are somehow viscoelastic, because you really have here the viscoelastic branch here in this mechanical model, and this single viscous part, where this usually is said it corresponds to solvent viscosity, and this viscoelastic element to some viscoelastic part of the structure in the fluid. So you can describe it by this set of equations that we will use. So we still consider it an incompressible fluid with this balance of momentum, where simply here for the stress tensor here we separate the pressure first from it, and then for the remaining part. I'm not saying it's spherical and deviatory because it's not completely true. It's true just for the Newtonian model, but this already Maxwell and Oldroyd models, we cannot say that the only spherical part of the stress tensor is in this pressure part is hidden also in this tensor. So here this tensor has zero trace, but this one doesn't. So it's a little bit more complicated. So this is a sequence of models that can be used, and this one will be most important for us because this is the standard, let's say, prototype of many viscoelastic models. Here, what is important is this kind of time derivative. It will be the time derivative, but evidently it's a bit different from this one because for the tensorial quantities, we need to use so-called convective derivative. And this is kind of a generalization of this material derivative that is typically used for vector or scalar quantities. This is just how to get the parameters of the model that are mentioned here. This time scales lambda 1 and lambda 2. This is said to be the relaxation time, and this is to be the retardation time, and this is the total viscosity. So you can get it from the mechanical parameters of the model, where you have the solvent viscosity, the elastic viscosity, and the Young modulus here. And basically from this you can get the two time scales that you need for your model. This is just for the definition of the convective derivative. So you can really see that the convective derivative of a certain tensor, in fact, is here. It's just not just one. It's not a unique choice. You have one parametric family at least, where this is the material time derivative, and then there is some correction for objectivity that depends on the parameter A. And here the W and D are the symmetric and skew-symmetric parts of the velocity gradient. So this together will give you the family of so-called Gordon-Showalter derivatives that depend on this parameter. And in the models that I will present today, there will be two of these derivatives used. Most of the time, the people use the upper convective derivative. And in the model that of the blood damage that I will show later on, this correlational derivative is used. It's really partly a matter of, let's say, physical arguments, which derivative to choose. There are some, I've seen some arguments why never use anything except the upper convective derivative, but the correlational derivative at least makes a sense in some situations. But from the computational point of view, it's just a matter of setting one parameter in the model, so it's not a big deal. But the response of the model and the behavior of the model is quite different, so it's really not something like to be forgotten. Here I'm mentioning 3 different papers on the blood damage. These are the main papers that I was using when trying to understand this kind of a problem. You should start probably from the newest, from this one, which is really the overview of many possible models of blood damage. The point is that the red blood cells are quite fragile and they can be damaged by different mechanical devices like blood pumps or artificial heart valves and this kind of things. And it's quite dangerous from a medical point of view to kill the red blood cells because they are really essential for life. So in order to be able to optimize the medical devices for the minimal damage of blood, we need to be able to assess the damage introduced to red blood cells by the mechanical devices. And there is plenty of models how to do that. I will try to explain some of them. So here this is the overview of many models. In the second paper, you can find the tensor-based, which means the strain-based measure for estimation of blood damage. And this paper, in fact, is based on something even older, which was not about cells, red blood cells, but about droplets and their deformation. So, in fact, in this paper for the blood damage, they are using some analogy with the deformation of droplets in the fluid. So this is classical picture that you can find in many of those papers where this is what they call the hemolysis index H, and it expresses the physical quantity. So this is the increase of hemoglobin concentration in the sample. So from the physical point of view, this increase of hemoglobin, free hemoglobin, this is the red color coming from the red blood cells, depends on some scalar measure of stress, this is the sigma, and the time of exposure. So longer you expose, the more it will be bleeding, and bigger stress, bigger bleeding. This is nice. This was verified experimentally with different set of coefficients here in this correlation, but it also has some drawbacks, as we will see later on. So this will just tell you locally what is happening locally, but the problem is that from the physical point of view, the increase of hemoglobin over the total hemoglobin can never be bigger than 1. But there is no such limitation in this model. It can grow indefinitely. So this correlation is widely used, but the coefficients are not, let's say, general. So you cannot use it everywhere without any limitation. So this is how to treat the problem in some intelligent way. So this is the correlation. Here you can see one possible set of coefficients. From this you can simply derive what will be the time rate of change of this hemolysis index. You just take a derivative with respect to time. There is nothing really special on this because this is really the exposure time. So this is the only change that you will observe. And then you can play with this kind of dependence. The trick is that you will take the original definition of age, and you will put it to the power 1 over beta. And so this is in the first step. This is what we will do here. So we will introduce a new quantity where this exposure time will be to power 1. And then with this new quantity, you will do what you did before with this one. You will take a time derivative and you will only get this simple relation for the rate of change of this, what they call the local hemolysis index. And then you will just replace this material time derivative by this expansion for your flow field. So in fact, you will get a transport equation for this hemolysis index with some source term that depends locally on the local scale and measure of stress. So this is the most primitive model. How can you get the assessment of the hemolysis index based on your local velocity field? From the velocity field, you calculate somehow the scalar measure of stress, you put it on the right-hand side of your transport equation, and you calculate in your device what will happen with this quantity that you can set the 0 on the inlet, like no damage, and you will calculate what will you have on the outlet. And based on this, you can already do some predictions of the hemolysis. It should be somehow improved because this is too primitive. There are many variants of this algorithm. Some of them are more meaningful, some of them less. The first meaningful modification is that you will only consider not all the stress in all domain, but just in places where it's, let's say, supracritical. So it's above certain threshold. Below this, you will simply switch off this source term and you will just solve the transport. So it will not contribute to the blood damage if the stress will be too low, which is quite logical. The other modification is, let's say, less obvious. The trick is to, because in the standard model, there's missing this term minus this h beta. But if you add it here, so it means it will somehow guarantee that the value of this h will not go over 1, which is the physical limitation. You can explain it by some kind of relaxation that depends on the local value. So it's not just increasing the blood damage, the hemolysis index, but it can also decrease in some cases. But the major role of this term is to keep it bounded from above by the value of 1, which is the physical value. Okay. So anyway, I don't think it's too important, at least because if you do here the differences between the principal stresses, then anyway, the pressure part will drop out and plays no role. So I don't see much of a meaning in this. But this is, let's say, how engineers evaluate some scalar value of stress from the complete tensor. They do it in many areas of mechanical or civil engineering. More mathematical way is to use the invariant of the tensor T, which you can do, but to my surprise, again, it's some kind of not unique. And different authors use, for example, again, this scalar measure of stress, where they are using here different coefficients. But evidently for different coefficients, you will get different predictions. And I don't know if they just need to publish something with a different formula. I really don't see any meaning in why to prefer one or another formula. There are some explanations, as usually in engineering, but there is no, let's say, definitive choice. So I'm just mentioning this to show that it's quite arbitrary how to treat the whole model. So this was the first large set of blood damage models. So essentially it works like this is borrowed from some paper. It's stolen from one of these 3 papers. I don't have the exact reference here. But the trick is that you get the stress tensor field, and directly from this you will get the hemolysis index. So you get the scalar measure of stress that you will put on the right-hand side of your transport equation, and then you will get the field of blood damage, let's say. But there is another new perspective set of models that are using some intermediate, they say intermediate equations before going to hemolysis index. So they are not going directly from the stress tensor field to hemolysis index. They want to bypass it somehow. And again, here is some explanation that I not fully follow, but it tells you the basic idea behind this kind of models. So this is how the true red blood cells behave. So as you have seen, these columnar structures at low shear rate, they are first broken into individual cells that are reoriented along the flow. Then they are slightly deformed and they undergo something that they call the tongue threading. I was trying to explain it somewhere that it really works like with the tongue, that the membrane rotates along the content. So you have here the red blood cell, and then the boundary rotates, but the interior stays at place. So really, if you take a tongue that is shooting somewhere here, so also here you can see that the chains are moving while the wheels are still at the same place. So this is simply a mechanism that appears at very high shear rates, and that it can be somewhat accommodated into this model. But I will try to skip it today. The major new thing here is at the end. So if this is not enough and we will keep increasing the stress, then of course, the volume of the red blood cells cannot change, it's incompressible, but what can change is the shape and the surface area. And there is a nice observation that if you increase the surface area by about 6%, then the red blood cell will stop bleeding and releasing the hemoglobin. So you can use this change of surface area inside of your hemolysis model. And how do they decided to do that is that they have used the analogy with droplets, where there exists a model for configuration tensor of a droplet, where they first consider the droplet to be spherical, and then they expect that it will keep the ellipsoidal shape, but change the orientation and change the stretch. And this is something that they want to use as the analogy to describe the change of surface area under shear rate. And based on this, to develop a hemolysis criterion and some hemolysis model. The way it is done in literature is a little bit complicated and quite long, but it uses completely without any change the original model for droplets. So you will write down an equation for tensorial quantity, where this is the droplet configuration tensor. Here on the left, you can see this corrotational time derivative. We are trying to filter out the rotation of the droplet from the equation. So this is, let's say, again, some time derivative, the time change of this configuration tensor, and then on the right-hand side, you have two terms, where there is explanation physical for both of these terms. The second one again, D is the symmetric part of the velocity gradient. So this is responsible for, let's say, the viscous response of the droplet or red blood cell. And this is some term that is responsible for the return to spherical shape or to the original shape from the deformed one. So this is, let's say, the elastic part, and this is the viscous part that affect the configuration tensor in this case. Again, this function Gs, G of S, is a scalar function depending on the invariance of the tensor S, namely the determinant, and then the second invariant of the tensor S. So if you expand this rotational time derivative, so it looks like this. So it works with the material time derivative, and then for the objectivity, there is this additional term that is just working with the skew symmetric part of the velocity gradient. So there's nothing coming from the symmetric part of the velocity gradient. And then you can also expand the material time derivative in this way. And finally, you will get this kind of a tensorial transport equation for this configuration tensor S. Going forward. Then what to do with this tensor, and then again, the standard version of the model says that you should try to, let's say, mentally apply it to a simple shear situation, where under this, you have this kind of velocity gradient. And if you do so, then you can calculate explicitly the eigenvalues of the configuration tensor just based on the coefficients and the intensity of the shear stress. So you can calculate it explicitly for the simple shear rate, and then you will observe that these eigenvalues are just squares of the semi-axis of the new ellipsoid that you will obtain in the under this shear being applied. And then you can play with this one. So you are able to calculate the new shape coming from the original undisturbed or spherical shape. And you can do it explicitly for this very specific flow field. And then they proceed in this way. They define the distortion index, which is just using the semi-axis of the new ellipsoid, the shortest and biggest. And from this, you will define this one. Again, evidently for the sphere, you will get this to be equal 0. So it's no problem. But again, you can calculate it explicitly. And then you can go backwards. So if somebody will tell you that I will give you the tensor S, you can calculate the eigenvalues. Then using this simple assumption of the simple shear, you can go back to calculate explicitly the shear rate. And this is what you can use to estimate the scalar measure of stress for your model. So it's somehow complicated way how to use the configuration tensor to go back and calculate in some non-arbitrary way the scalar measure of stress. It's not perfect because it's really using the hypothesis of simple shear, but at least it's something that will give you something, let's say, meaningful and based on physiology of the cells, and not just on some arbitrary guess. So you will get this one. You will put it in on the right-hand side of your transport equation for the hemolysis index, and then you proceed like for the stress-based models. The problem is, of course, that you have to solve this equation for the tensor S, which is quite time-consuming, but the advantage is that you can do it a posteriori after you have your velocity field. And even if this was derived under the assumption of Newtonian fluid, you can use virtually the same technique for non-Newtonian fluid. Simply, if you have the velocity field, you can solve the transport equation for the tensor S and evaluate all the terms. So this is the advantage. So it can be done, and it can give you some prediction. It's of course much more expensive than the original model, where you have just some simple formula for the scalar measure of stress, but it's doable. And this is the a new trend, a new fashion in this blood damage modeling. But when I saw the equations, I realized that I saw the equations already before, but in different context. This droplet configuration model was very similar to model that I've seen and solved previously, which was the reticoplasm viscoelastic model for description of blood, which is described in these papers and many others. And Rajagopal is working with so-called natural configuration in the continuum mechanics. So he doesn't only has the reference and current configuration for describing the changes in continuum, but he has some extra so-called natural configuration, which he states it's a stress-free configuration that is reached by instantaneously unloading the fluid parts of the continuum from the current configuration. It's not so important. What is important here is that the whole model is formulated using not the stress, but the stretch, and mainly the left and right Cauchy-Green stretch tensor. This is the description that you can find in the paper, either his or mine, previously. But if you take a look at the model, how does it work? So what you can see in the model is that it's based on some thermodynamic assumptions using stored energy, rate of dissipation, and the stress power coming from the, again, the symmetric part of the, also the gradient and so on. So here the time rate of change of the stored energy depends on the stress power and the rate of dissipation. And using this framework, you can derive models for different materials. What is interesting and important for us is the structure of the model and the structure of certain terms in the model. For example, again, this one, for this neo-PN material, again, this is a kind of a term that we have previously seen in this droplet model, which was responsible for the return to the spherical shape. Also here, if you will have this stretch tensor will be just identity tensor, so the trace will be equal 3. So this will disappear and there will be no force in the model responsible for this. And again, like we have seen previously in the model for the tensor S, here we have some time derivative. In this case, it's upper convected. Again, this tensorial derivative, and here some source term on the right hand side, where again this one comes from the elastic response of the material. So there is the whole machinery developed for this kind of materials. What is interesting and nice is the viscoelastic model for blood, where the complete stress tensor again consists of the pressure part. Then there is this elastic part coming, or viscoelastic, coming from the previous slide that was just described, and then there is the other branch with the solvent, just purely viscous response. So this is kind of equivalent to this previously seen Aldrich model, but is quite highly nonlinear model that can even be generalized for the shear thinning effects using this definition here. So you can write a code and solve this kind of a model. So it works like this. So this is again the complete stress tensor. Here you have the pressure part, and this comes from the viscoelastic model, where this viscoelastic stress is divided into two parts. This corresponds to something like the Maxwell viscoelastic model, and this like the Newtonian or Stokes model, if you want. So this is purely viscous. This is quite a boring part. But even if these two terms look very similar, the physical meaning of these tensors is completely different. This comes from the velocity gradient, but so it has something to do with the rate of deformation of the continuum. But this one, this is really the left Cauchy-Green stretch tensor. So this is really something about the deformation. So it's somehow similar to what was developed previously for this deformation of the droplet. So the whole idea here is whether we can or cannot use this information that we are already getting during the calculation of the rheology of the model, if we can also use it to assess the blood damage without solving any additional, let's say, tensorial equations. So first, if you try to expand this Radekopal's model, so here you have this is how it is written somewhere in his paper. So this is the upper convective time derivative of the stretch tensor. Here you have some coefficients. This is the important part. Again, it corresponds to this elastic response and return to the spherical shape or unloaded shape. And if you expand first the upper convective time derivative using the full velocity gradient, and you plug in all the coefficients, and these are the data that Radekopal is giving for blood, because it really predicts also the shear thinning. So it was fitted to this kind of a data for this zero and infinite shear rate viscosities. Then you can play and rewrite it in this way. So these are the coefficients, and there's some function that you can call tau, just to be consistent with the other model that I will be showing. So all these coefficients you can sum up into a function that depends on the tensor. So it's kind of a nonlinear function. So it's not a constant, but otherwise this is quite a simple form. And then you expand the upper convective derivative here, we simplify the right-hand side, and you can recast everything into this form. The trick is that if you write it really in this form, it looks very similar, almost identical as the Oldroyd B model that we have previously seen at the very beginning of the lecture. The only difference is in definition of these coefficients lambda and tau, that have different meaning in both models. Otherwise, computationally, it's exactly the same like Oldroyd B model. So there's nothing really special and new, except these nonlinear functions that you get for the coefficients of the model. So if you compare the Oldroyd B with this Radekopal's model, so this is the new Radekopal model, and this is the very old Oldroyd B. For the Oldroyd B, these coefficients tau, let's say these functions here before the source and sink terms, these are constants, unless you really want to make it shear thinning. In Radekopal's model, both lambda and tau are functions, but otherwise it's exactly the same model. You don't have to change even a single piece of your code. You can really apply it. But it's of course not so easy, because there is a different, let's say, physical background behind the model. So when I was trying to solve it, then if you solve the stress tensor model, so you can see that because of the incompressibility, the trace of the symmetric part of the velocity gradient should be equal to 0, which results into the requirement of the determinant of this stretch tensor to be equal to 1. But when I was trying to solve it, but I was solving it by finite volume method and artificial compressibility method. And you know, the artificial compressibility means that you do not satisfy exactly the divergence-free condition all the time, just in the final limit. It was causing a lot of troubles, leading to the fact that the determinant of this tensor wasn't equal to 1. So it was not preserved during the simulation, and already this led to troubles. Here's just some explanation that the tensor B it not only has, again, it should be symmetric tensor that is positive definite and has the determinant equal 1. It should be. And in the simulations to define the coefficients, we are also using the trace of this tensor for some reason. And if there is some, let's say, undershoot somewhere or overshoot, you can come into troubles and divide somewhere by 0, or come very close to dividing by 0. especially in these terms, it's quite tricky. So to overcome this problem, I was trying to figure out and design some modification of the computation algorithm. And finally, I came up with something that seems to be strange, but it's very elegant and efficient, finally. So this is my complete stress tensor, again, pressure part, which is just constant times the unit matrix or tensor. Then you have this stretch part, and you have this standard traceless part of the tensor. So the trick is that I would like to have the determinant of B equal 1, and it is not. So what I will do is that I will borrow part of the pressure, and I will add some, let's say, epsilon times the identity tensor to my already existing stretch tensor here. So I will simply just shift the diagonal elements of this tensor by some small epsilon that I borrow from pressure. The advantage is that, as you can see here from this expansion, you are not really changing the total stress. So it has no immediate effect on your velocity field, but it will allow you to fix your stretch tensor and to preserve the determinant to be equal 1. And the pressure is then updated in the next iteration. So if you try to find what should be the correct epsilon in this algorithm, so you will start from this kind of equation. So after you add this epsilon times identity, you would like to have the determinant equal 1. And if you expand it using the invariance of the tensor B, you will come to this almost like characteristic equation that you need to solve for epsilon. And evidently, it's one of the possible ways is to use the Newton's iterative method. So if you do it, you will get this very simple iterative algorithm for obtaining the correct correction factor epsilon. But again, if you just start from epsilon equals 0, like the initial approximation, you will get this for the initial guess for a correction factor. And in fact, it's enough just without any further iterations. These are really just small corrections, and we are looking for the steady state. So if you employ this correction and you will add epsilon times the identity tensor to your tensor B, then your tensor is perfectly corrected. You didn't broke up your velocity solution because you have stolen just a piece of pressure and move it to your tensor from the pressure field, and it's done. So there is no need for sub-iterations or something, at least when we are looking for a steady state solution anyway. We just need to keep the determinant of the tensor B under control. So it works surprisingly well, and it's very elegant and simple way how to fix the whole algorithm. But then if you come here, so if you compare the two models, the droplet configuration model that was already used for the blood damage, then you will get this kind of let's say tensorial transport equation for the configuration tensor S. Where with these parameters, where this F1 is 1 over some time scale, where this time scale is given somehow, or can be measured from the oscillations of the red blood cells and so on. And these are the parameters. And this is the scalar function that is, as I said, is some kind of elastic response that tends to return the droplet into original shape. So this is the original model that was already solved and used for the blood damage. And this is the Rajagopal's model that is used for rheology, never for the blood damage, but for rheology. So if you take a look at this model, then you see that you have there exactly the same terms. Again, if you already have a code for one of them, so just by change of coefficients, you can use it for the other simulation. And it's really kind of surprising that even the coefficients and the source terms, they look the same. They have they have the same, even the physical meaning. It's some inverse of the time scale here and so on. And also here you are using the invariance of the tensor. So the idea is, if I do already have a code for this tensor B calculation, even if I'm using it for description of the rheology of blood and not for the blood damage, if I can reuse the information for the blood damage assessment. Here is first I'm repeating the droplet configuration model, how does it work and how the tensor information is used to assess the blood damage. The trick is really to calculate a posteriori, after your velocity field is solved, you will calculate this tensorial equation for this configuration tensor. From this, you will calculate pointwise the eigenvalues. I will come to this later on. And from this, you will get the semi-axis of the deformed ellipsoid, from which you get the distortion index, from which you estimate the scalar measure of stress. And then you plug it into your Eulerian reformulation of your hemolysis correlation. So again, you have transport equation for this modified hemolysis index with the source term depending on the just calculate the scalar measure of stress. After you calculate it, you will just put it to power eta, and you have backwards the hemolysis index in the physical meaning and units. Then you just integrate over your inlet outlet to see what additional hemolysis comes from your medical device or from the blood pump or something like this. So the question is if we should proceed the same way for the tensor B. And the answer is we can, but maybe we shouldn't or don't have to. The first major difference is that my tensor B comes together with the velocity field, and it affects the velocity field. It is used to obtain the velocity field. So it's really coupled to the velocity field, and you can, so it's not just kind of post-processing after you calculate your velocity field. It's used to obtain, and it should be solved together with the velocity field. What you can do, you can proceed as for the tensor S. I think it will be roughly the same story, but there is another possibility that was not tested yet and that I'm willing to test. And it's to first again calculate the principal stretches. From this, you will get the semi-axis of the deformed shape. And then what you can do, because there is this experimental measurement saying that if your surface area of your red blood cell will increase by about 6%, it will start bleeding. But then if you take, okay, originally the undistorted shape was this one, and I will just do a small distortion. So from sphere, I will distort to ellipsoid, so I can compare the surface areas. If I have, because for the sphere, this tensor B will be just unit tensor. So sphere of radius 1, it's easy, then you just need to evaluate the surface area of ellipsoid, for which you know the 3 semi-axes. And you compare them. And if this increase will be about 6%, so it means this relative area change will be greater than this 1.06, then you will activate the source term on the right-hand side. What should be the source term exactly? It's kind of a question, but still you can use something that comes from this hemolysis correlation. But its nice trick here is that there is no ad hoc heaviside function saying where to switch on or off this source term. It's something that comes from the geometry of your cells. But then, so this is the almost final idea how to do that. But still, there are 2 problems how to proceed with this algorithm. The first one is that you need to really find the 3 eigenvalues of your tensor. It's symmetric, positive, definite tensor, but you need all of them. And if you try to do it in some by some formula, then it might be complicated and prone to errors, numerical errors, I mean. So this is one problem, and second problem is that maybe I'm stupid, but I always assume that there exists a simple formula for the surface area of ellipsoid. The fact is that it doesn't. For a sphere, yes. For a rotational ellipsoid, yes. But for general ellipsoid with 3 semi-axes being different, there is no intelligent formula to use. So first, the problem to solve the eigenvalues of the tensor B. Anyway, we only need some estimate. So if you just imagine that this tensor B is symmetric, positive, definite, and it's just perturbation of a unit tensor, then what you can do at the first approximation is to say, okay, the off-diagonal elements are negligible and the eigenvalues are very close to the diagonal elements of my tensor. So you can theoretically use this kind of approximation instead of solving some roots of cubic equation at each point. So you will just take your diagonal elements. So this is big time saver. Then the second is with the surface area of the general ellipsoid that is not rotationally symmetric. And I found this formula that was tested numerically that is quite accurate, at least for the purposes that we will need. So what you can see is that if all these semi-axes will be equal and equal r, for example, like radius of a sphere, then from this you will get exactly the formula for the surface area of a sphere of radius r, independently of this factor alpha, this power alpha that is used in this formula. And this alpha is just used to get the best possible fit for a wider range of the semi-axes. And they suppose something like this in general, and some special values in case that you have some idea about how your ellipsoid looks like. I think for the ellipsoids that are close to sphere, they say that you can use something like 8/5 or something like that. And the error in the surface area is about 1% with this very rough and brutal approximation. So it's, again, quite nice thing. So this will just give me that if I divide it by the area of sphere, I'll just get rid of this factor 4π, and I will end up with this formula. So simply, I will switch on my source term in the case that I will see that this value will be greater than this magical 1.06. And if you, moreover, consider this this stupid thing, so you can directly, without playing with it, with some eigenvalues, you can plug it in here, the diagonal elements of your stretch tensor, and you will get very simple criterion that if you already have the stretch tensor calculated for your velocity field, you just put it there, and you don't have to solve this configuration tensor S or something similar. So this is basically how to do that, and I think there are just conclusions and so on. So I did some overview of the blood damage models that are very important, and it's a very challenging topic, and there is not a general consensus about how to model this phenomena and what are the factors that are affecting this blood damage. For example, recently I've seen that they are trying to consider not just the standard stress in laminar flow, they are trying to consider the flow to be turbulent with turbulent fluctuations in the stress to be responsible for some peaks in stress that can exceed the stress threshold for the damage of the red blood cells. So they don't even know if it should be considered as turbulent or laminar or time average, or they really need the whole statistics of the flow or something like this. So in this context, the general idea about using strain or stretch-based models instead of stress-based models seems to be quite natural and good idea, because you will bring more physics into the model, and there is less ad hoc assumptions that are just done by engineers just to get some results. And evidently, I will try both this tensor S and tensor B. And my final goal is to compare the predictions of the two models. The advantage of the S-based model, this configuration tensor-based model, is that you can use it in the post-processing step for any model of the fluid. Doesn't matter if it is Newtonian, generalized Newtonian, viscoelastic, maybe, still you can use it. Maybe it's not perfect, but still you can use it. But this one is really specific for the model of Raja-Gopal with this, where this stretch tensor is already calculated and used. So it's kind of limiting factor. But the good point is that when you calculate this stretch tensor, you use it both to affect the velocity field and to evaluate the red blood cell damage. Then I was discussing already some of these problems. What is nice is this areal strain threshold to be applicable instead of the stress threshold, because it's again something that is, let's say, physically and experimentally documented. So if the area of the membrane goes over certain value, then it will start releasing the hemoglobin. There can be made one more conclusion after this, because in fact, the open question is what to do if I will have viscoelastic model, but not the Raja-Gopal's one. But if I will have just the older B model, can I do something similar? And maybe you have seen the people who are solving this high Weisenberg number problem using the conformation tensor. So it's just a reformulation that instead of the stress tensor, you have the conformation tensor, which is again some kind of a measure of local deformation. So maybe, again, it's a symmetric positive definite tensor. So maybe again, what we can do is from the eigenvalues of this tensor that you need anyway if you are losing the logarithmic transformation, you can again calculate the areal strain of the cells and use it for estimation of the blood damage. And it's almost for free. You already have the tensor, you did already the major part of the work. So the final goal for this set of work is to have three models, to have the S model with the configuration tensor, the B model with try the same approach for the conformation tensor based reformulation that is applicable to all the viscoelastic models. And I think that is end, and there is just the list of the papers that I've been using in my explanation. So that's it.